Hello everyone, myself Michael Ravina, Associate Professor, Department of Computer Science and Engineering. The subject is CS 3551 Distributed Computing. The unit is Logical Time and Global State. In this video, we are going to discuss about vector time and physical clock synchronization, that is NTP. Vector time. The system of vector clocks was developed independently by Fitch, Matten and Smuck. In the system of vector clock, the time domain is represented by a set of n-dimensional non-negative integer vector. Each process Pi maintains a vector, that is Vt of 1 to n, where Vti of time I is a local logical clock of particular Pi and describes the logical time progress at process Pi. Vti of j represents the process Pi's latest knowledge of the particular process Pj local time. If the Vti of I is x, then the particular process Pi knows the local time at process Pj has progressed till x. The entire vector Vti constitutes a particular process Pi's view of the global logical time and it is used to timestamp events. Vector time. The process Pi uses the two rules, that is R1 and R2, to update its clock. First, R1. Before executing an event, process Pi updates its logical time as follows, that is Vti of equal to Vti of plus d. The d value is always greater than 0. Next, rule 2. Each message m is piggybacked with the vector clock Vt of the center processing at the time. On the receipt of such a message m, Vt, the process Pi execute the following sequence of action. First action is the updates its global logical time as follows, that is the k value is always between 1, 2 and n, and Vti of k equal to maximum of Vti of k, Vt of k. Vt means that is a vector time. Next one is the execute rule 1, then deliver the message particular m. The timestamp of the event is the value of the vector clock of its process. When the event is executed, the following figure shows an example of vector clock's progress with the increment value d equal to 1. Initially, a vector clock is 0, 0, 0, 0. This is the example of the vector clock. Here the evaluation of vector clock time, the vector clock time is represented as this manner. Here there are three processes involved in this particular properties of vector time. The vector time has the following properties. First one is isomorphism. If events in a distributed system are timestamped using a system of vector clock, we have the following property is if two events x and y have timestamps vh and vk respectively, then x tends to y. That means vh greater than vh is less than vk. Suppose if there is x combined with y, that means vh is piped with vk. Thus, there is a isomorphism between the set of partially odd and even produced by the distributed computation and their vector timestamps. Then second property is a strong consistency. Then third one is the even counting. Strong consistency means the system of vector clock is strongly consistent. Thus, by examining the vector clock of two events, we can examine they are causally related. Then even counting means if d equal to 1, then in the rule 1, then the ith component of the vector clock at the process is Pi and Vti of, that is vector time of particular process Pi is the I. Vti of I denotes the number of events that have occurred at Pi until that instant. Then physical clock synchronization NTP. Clock synchronization is a process of ensuring that physically distributed process processes have a common notion of time. Due to different clock rates, the clocks at various sites may diverge with time, and periodically a clock synchronization must be performed to correct this clock skew in distributed systems. Clocks are synchronized to an accurate real-time standard like UTC, that means Universal Coordinated Time. Clocks that must not only be synchronized with each other but also have to adhere to physical time are termed physical clocks. These are some of the definitions and terminologies used in the NTP. Let's take CA and CB, the two clocks. First, time. For the time definition of time is the time of a clock in a machine P is given by the function of Cp of t. The Cp of t equal to t for a perfect clock. The next one is the frequency. Frequency is the rate at which the clock progresses. It can be represented as Ca of t. Offset. The clock offset is the difference between the time reported by the clock and the real time. Skew. Skew is the clock is the difference in the frequencies of the clock and the perfect clock. Drift. That means the drift of the clock Ca is the second derivative of the clock value with respect to time, namely Ca double dash of t. That means second derivative of the particular clock. Then next one is the clock inaccuracies. Physical clocks are synchronized to an accurate real-time standard like UTC. However, due to clock inaccuracy discussed above, the timer clock is said to be working within the specification. That is 1 minus rho less than or equal to dz of, that means the particular differentiation function is involved. Then the next figure illustrates the behavior of the fast, slow and perfect clocks with respect to the UTC. This figure shows the behavior of the fast, low, slow and perfect clock. Suppose if it is a perfect clock, means the particular differentiation of dc by dt equal to 1. Suppose if it is fast, means it is always greater than 1. Slow means it is always less than 1. Then offset delay estimation method. The network time protocol, which is widely used for clock synchronization on the internet, uses the offset delay estimation method. The design of the NTP involves a hierarchical tree of time servers. First one is a primary server at the root synchronizes with the UTC. The next level is contains the secondary servers which acts as a backup to the primary server. Then next level is at the lowest level is the synchronization subnet which has the clients.